So this is the heat transfer in forced convection apparatus. So we are going to find the heat transfer coefficient in a forced convection. And here this is the test section. And in test section, 3 thermocouples are connected to it. And after the test section, that is at the exit of this test pipe, there is a thermocouple. And before the inlet of this test section, there is a thermocouple. And this is the heater. And we are having a blower so that we are able to obtain the forced convection. So what we do is, in total, we are having the 5 thermocouple. So T1 and T5. T1 is the inlet condition. T5 is the exit condition. Thermocouple of the inlet and exit. And 2, 3, 4 represent the thermocouples at the surface. So now, if we are able to obtain this T1 and T5, we can get the average of T1, T5 such that we are able to get the average temperature of the air flowing through it. And average of T2, T3, T4 will give the average surface temperature. So we are able to get the surface temperature and we are able to get the temperature of the air. That's what we do here, and we will be substituting it to get the heat transfer coefficient. Now here, first this is the main switch. Then after main switch, this is the blower unit. For switching on the blower unit, what we are doing is, first we will be switching on it. Then there is a lock so that we are able to permanently keep it in the on state. So blower is on. Now this is the dimmer for this one, blower. That means now blower is on, and by now first initially this should be kept at the 0 position, and after that we will be adjusting it, and on adjusting it this blower will start working and air will be flown out of.
We can regulate the flow from the blower.
Okay. So as we increase this flow, what happens is there will be a level difference in this U2, and because of that level difference we are able to note the level difference. So let us say that here the reading is H1 and here the reading is H2. So we should set this blower at a position, this dimmer at a position, so that we are able to control the flow at a given level difference. It will be given in the question, the flow will be at this much height level difference. So we should keep that. Then after that, what we do is, initially we will be taking this T1, T2, T3, T4 and T5, and then after every 10 intervals we will keep on taking reading, and at a time this T1 to T5 reading will be same as that of the previous set, and at that state we can say that our entire apparatus is in steady condition. And now we have readings. So now take the average of T1 and T5. So we are able to get the temperature of this air. Then T2, T3 plus T4 by 3 we will get the surface temperature. And here this heat transfer coefficient is QA by A into TS minus TA. So TS, surface temperature, and TA are obtained. A is the surface area, that is the curved surface area of this particular test section, and that can be obtained by here diameter of the pipe and length of pipe are given. So we are able, by pi dl we are able to obtain the curved surface area. Now then QA means it is the heat supplied, that is QA is equal to mCp into delta T, where m is the mass flow rate of the air. So mass flow rate of the air, for finding the mass flow rate, we are having the height difference, the level difference, that is h, and that h is substituted in this equation. Here we are having CD, that is this one, coefficient of discharge, then pi by 4 into d square. There will be a particular orifice meter here. There will be an orifice, and the value of diameter of that orifice should be substituted here. So into 2g into rho w by rho a into h by 100, we will be getting the volume of discharge. Then that volume of discharge, when we are multiplying it with the density, we will be getting the mass flow rate. So into Cp is heat constant pressure, and into delta T, specific heat at constant pressure, into delta T. Delta T is Ts minus Ta. We are able to get Q. So now by substituting the known values here, we will be getting the heat transfer coefficient in this forced convection. Similarly, here we have T1 and T5. So we will be getting an average temperature. So from tables we are able to find this one average kinematic viscosity of that particular temperature, and then we will be substituting that here. V d by mu. Here d is the diameter of the pipe is known, and V means V is the velocity of air. For finding the velocity, what we do is we are having the volume. So that volume will be divided by the cross-sectional area. We will get the this one. We will get velocity. So that velocity will be substituted here, and now we are able to obtain. So here, volume divided by cross-sectional area. So we have velocity, this kinematic viscosity, and we will be substituting d, and then we will get the Reynolds number. So this is how we find the heat transfer coefficient and Reynolds number by using given apparatus. Thank you.